Hello, this is Hodges Haywood. This is my presentation for my CS230 project. My task was to build a neural network that could classify the condition or physical status of a parcel package on an automated conveyor system. My motivation is that basically everyday logistics companies like UPS and FedEx lose millions of dollars as a result of damaged packages. So these packages flow through distribution centers with miles of conveyor belts. They're at risk of becoming crushed, breached with holes, or open. These packages might contain vital medicines or hazardous materials. Currently, systems are being monitored manually, which increases the possibility for errors and limits scope. Because humans, as we know, make mistakes, and we can't see everything and we can't be everywhere at one time. So I propose to build a neural network classification system that could detect whether a package is damaged or not. Maybe future work would be to connect for me at least, would be to connect the neural network to a camera and test it out, and sort of in a real world situation, and maybe place cameras strategically throughout a system. For instance, this picture here is a picture of an automated conveyor system at UPS Smart Hub. And all these green lines and curves you see are miles and miles of conveyor systems, conveyor belts. So you can imagine at any given time, a package can become lost or damaged. And since humans can't be at every point on the conveyor system, these packages are at risk of being damaged without anyone actually knowing about it. So I think it would be a good idea to, create a neural network that could actually be strategically placed along these conveyor belts, and then they could actually monitor the belts and keep an eye on the system and determine whether packages are damaged or not. So let's move on. This is my data set and pre-processing. Here are some examples of some of the packages in the certain states. Like these here on the top are packages that have been damaged. So these are the ones we really want to detect and catch ahead of time and get them off of the conveyor system and take care of the problem. And these are packages that have not been damaged, and these are in pretty much healthy condition. So my method was I used 5 neural network architectures. I used a baseline, just a simple convolutional neural network, and I also used a baseline with augmentation and dropout. And then I used transfer learning with VGG16, ResNet 50, and an Inception V3 on a fully connected head, if you will. And my hyperparameters include different epochs, different learning rates, dropout, augmentation, and transfer learning. And these are my results. The test results are not stellar. I think this might be kind of high bias. I don't know, but my training accuracy, say for instance on the baseline model was 99%, and the validation accuracy was 80%, whereas the test accuracy was 25%. And as we go down the line, we can see that my for the baseline with augmentation and dropout, the training accuracy was reduced. As well, and the validation accuracy went up. And then for VGG16, my accuracy on my training was 84%, validation was 88%, test accuracy went up to 48%, and this was with transfer learning. And ResNet 50 brought the training accuracy up to 89%, validation accuracy up to 50%, and the test accuracy was 50%. And this is transfer learning. And the same thing with Inception version 3. The training accuracy was 77%, validation accuracy was 67%, and the test accuracy was 50%. And here are some graphical representations of the accuracies and the losses. And then I have confusion matrices to kind of tell a little story about how the data the images were misinterpreted by the different models. Um, and then I used visualization of layers just to try to get an idea of what was happening in the different layers. And I kind of feel like these really don't tell me too much of a story because it looks like there are highlights all over the place and I don't see any specific activations. But it still kind of give me the idea that, you know, the models didn't really generalize that well to the test data. And this one here is for just just a baseline. No hyperparameter fixing or anything like that. Whereas this one here, the baseline model with augmentation and dropout, it's a little different. Things look a little more opaque on the visualization of the different layers. So my conclusion that my models perform well in training and validation, but not too well in the test images. It looks like there was a high variance between the validation and the test data. Dropout seemed to help a little to prevent overfitting, and I know I need more data and better pre-processing. So there's a lot more room for improvement of performance of the models on the type of data that was tested. So this was expected. In the future, I could probably use bounding boxes around specific regions of damage on the boxes, and that might help with the activations, and it might help localize, what the neural network is actually supposed to do. So my future work, more processing of the images by putting bounding boxes around the zones of damage and labeling them, collecting much more data. I think that would help. And explore applications to other practical areas such as food quality or something like that. And again, going back to my data, shows here that I used 2000 RGB normalized training images, 200 RGB normalized validation images, and 200 RGB normalized test images. Probably would have been done a better job with more test images. And then also, like I said, labeling the images with bounding boxes or something like that. So thanks for listening to my presentation and have a great day.